is phi. And if one takes the composition of this particular map, this is nothing just the identity of X. So this is the topological definition of the retraction of the topological space. The same concept is being taken in the algebra. And we say that the two algebras, K algebras, A and B, are said to be are satisfying this condition. Firstly, has an embedding inside B, and we have an injective homogeneous K algebra homomorphism. So I assume my maps are graded. Okay, it is better. So I assume my maps are graded. So that's why I use this particular word, homogeneous K algebra homomorphism. And A is called an algebra retract of B with the same condition. If there exists a reverse map from B to A, which I mentioned with pi, with the same condition, pi of I is the identity of H. So I hope the definition is clear. So in this particular scenario, we say that A is an algebra retract of B. This is the formal definition of algebra retraction. And this is the same if you would like to see it from the topological sense. The one has to take care that the map is the graded one. Okay, note that it is not necessary that homogeneous homomorphism are of degree 0. So mostly in commutative algebra, building resolution, people do the shift of the degrees to make the maps of 0 degree, but here it is not necessary. So in general, because this is an introductory lecture about this particular problem and the background of it, so I will explain about. So in general, it is really very hard to decide if A is contained in B, whether there is a retraction, there exists a retraction or not. So in other words, the existence of this map phi is a quite non-trivial and quite a hard problem in algebra. In topology, things are much nicer, but in algebra, things are not. So different studies has been done in constructing the criteria. So people have been working in addressing this particular problem. And there are different criteria to decide whether a given inclusion X to Y has an algebra retract or not. So this is basically the slide is not visible. So let me, yeah. So this slide is basically, you have seen the definition of algebra retract. So the first question which can come into your mind, what are the intriguing questions concerning to this particular definition? So firstly, finding the criteria for algebra retraction is one of the hot problems in algebra. People are trying to construct new criterion to address this particular issue. So sometimes people go from one area to the other area, relate some combinatorial property to address some criteria to come up with retraction. And similarly, many researchers investigated the behavior of algebraic properties of B with respect to A. So for instance, just like in topology, if there is one space, then there is another topological space. What properties of this particular space carried to this particular space, who is a retract of that particular space? So just the similar is regarding to the algebra. So people are trying to address this particular problem. Then okay. And characterizing all possible algebra retract. So if you are given with a given algebra and you are asked to characterize all possible algebra retract of that particular given algebra, this is also among the central problem in commutative algebra. Let me just introduce you one of the central problem in commutative algebra and algebraic geometry, which is related to this particular problem, is the famous Zariski cancellation problem. Zariski cancellation problem is one of the fundamental problem in algebraic geometry and commutative algebra. And what is the statement of this problem? The statement of this problem is something like that. So it is among those problems in algebraic geometry which are very simple, and many people think they are quite trivial, but they are not. And this is a perfect example of it. So Zariski cancellation problem says that if R is a K algebra, where K is a field, such that Rx is isomorphic with this polynomial ring with n greater or equal to 1. So is it true then R is isomorphic to one variable less? So if you drop this variable, so I drop this particular variable. So many people, I think, including myself, when I was studying algebraic geometry, I always see this thing as a trivial object, but this is not so trivial. And let me just tell you, up till now, there is a proof which is known, which is given in 2008 by Karishola and Limanov, and they gave an answer to this Zariski problem for k characteristic 0 in the case when n is equal to 1 and 2 variable. Only for n is equal to 2, the problem is known affirmative. For n is equal to 3 and onward, it is still open. And one of very famous mathematician from India, Neena Gupta from Indian Statistical Institute, she gave an answer when the characteristic of K is positive. In that particular case, she gave a negation. She gave a proof. And by the way, for this particular proof, she got a lot of fame. She got different awards, including the ICTP award, which is dedicated to women in sciences, promoting women in sciences. And similarly, in India, she got Ramanujan Award for giving the proof, independent proof of uh, for this particular case. But this case was very important because in the positive characteristic, she gave a proof that this is not possible. Zariski cancellation problem claim does not hold for n greater or equal to 3.
But why it is not trivial? Because it feels like trivial problem. It is some kind of hypersurface.
I will explain. This is the main crux. So this problem has a strong connection with algebra retract. I'm bringing you this. So, and uh, over the characteristic 0, the problem is still open for n greater or equal to 3. So this problem has strong connection with algebra retract, but I explained you the give you the definition, and the definition seems to be quite simple. But I told you that constructing the map phi in algebra is the really hard problem. Yeah. It's not true. Yeah, she gave a negation of the because that was a conjecture. Is it true? Is it true? Then so she gave a negative answer to that. So either a conjecture is proven or disproven in any case. So she didn't give a counterexample. Her proof was completely based on multiplicative ideal theory. She worked on the ring coming from the ring aspect. And okay, well, this is a good time to popularize our John Conway Spirited Seminar Series. She has been one of the speakers of the John Conway Spirited Seminar Series where she presented that paper. And the presentation is on the website, recorded. And moreover, the paper is on archive. The paper does not require very special skill. Anyone who are good with ring theory, K algebra. So her approach was completely algebraic. She didn't use any special tools from algebraic geometry in order to disprove this result. Okay, and because directly attacking is of this particular problem, people have been trying. Okay, one of the reason why algebra retraction is so important. I told you different central problems in commutative algebra, and one of them is the Zariski cancellation problem. Then there was a very classical paper by Costa, and that paper appeared in 1977. And Costa proposed even stronger question. So the question Zariski gave is for the polynomial ring. And what Costa asked, now this problem is known as Costa's problem. And that problem says that if R is an algebra retract of a polynomial algebra over K, then R is isomorphic to a polynomial ring. So in that case, you just need to drop a variable at this case, but this problem is even harder. And by the way, there is a series of open problem and conjecture which revolves around this particular problem of algebra retract. And this is a problem which is known as the Costa problem. Again, in mathematics, if people are trying to attack a particular problem, so they try to construct different problems which address the same problem, but people can attack it from different tool. So Costa's problem is among those. And this anyone who solved the Costa problem, how it resolved the problem, Zariski cancellation problem, is this one. If n, okay, by the way, Costa himself in that particular paper, he proved this particular problem for n less than or equal to 2 in his paper. And this is, you can say, 5 years now. In 2018, I used to say this is quite recent one, but anyways, there's a Japanese mathematician whose name is Takanori Nagamai. He gave he gave a very important connection between Costa's problem and Zariski cancellation problem. He says that if you prove the Costa's problem for n plus 1, so it gives an answer to the Zariski cancellation problem for n. So one step ahead of the Zariski cancellation problem. So this is one thing. So if you prove the cancellation Costa's problem for particular value of n, so it means you are proving the Zariski cancellation problem for n minus 1. And moreover, in the same paper, he proved the Costa's problem for n is equal to 3. You can see that Costa himself already gave a affirmative answer for n greater or equal to 2. So he improved two step. And by the way, no progress in terms of the Zariski cancellation problem. Zariski cancellation problem is known for n less than or equal to 3. N less than or equal to 2. So greater or equal to 3 is still open. So he gave an independent proof of the Zariski cancellation problem, but by using the Costa's problem. Okay, I hope you are following the story up till now. Okay, this is one aspect. So Costa problem is also one of the central problem, which is giving an answer to the Zariski cancellation problem. So now, what kind of preservance problem is being studied, and what are the interesting algebraic research happening in this particular direction? So since a retract of ring, both subring, homomorphic images, so several properties of the ring are preserved. So if you are assuming a particular ring and you are taking the retract, so this is one of the problem, which kind of property, just like Harry did from original ring to its retract. So several properties are mathematically known in this particular context, that if the bigger ring has some properties, then the retraction has the similar kind of property. Okay, before moving, opening up all the results, this is quite a strange problem. If someone give an answer in positive sense, that this is an algebra retract, this is important. If you give a negative answer to that, even deciding there does not exist a retract, it is equally hard problem. So, and that is also valuable. But you have seen in the case of Nina Gupta, she gave a negation. This is also equally important, even with the case of algebra retract. So if B is an integral domain or Noetherian, so are its retract. So these are some known results. If B is Noetherian, so all its algebra retract will be Noetherian too. Moreover, evaluation ring is the one whose rings whose ideals are totally ordered by Euclidean. So definitely that the retraction preserved, because it's all about the interplay of the homomorphism, and the fourth isomorphism theorem indicates that the lattice structure will be the same. So that particular thing transfer to any of its retraction. Moreover, if X is a family of indeterminates, then A is a retract of AX, and also the formal power series ring of it. So these are some results from the ring theory, of, where people are discussing about the preservance properties under the retraction. And you might be thinking about whether 0 is an algebra retract of any non-trivial ring. So the answer is no, 0 cannot be, because we are assuming non-zero homomorphism here. This is the most important point as a K algebra. So there is a very important result given by Costa in the same paper that says that if A and B are the two rings, then the following properties are equivalent. The first property says that it means that F, there exists an idempotent homomorphism from B to B, and under that particular condition, F restriction on A is the identity one, and this particular condition is equivalent of saying that B is equal to A direct summand with I, where I is an ideal inside B. So by the way, all these results and all these approaches are being, I will unfold few more results where people are trying to construct the retraction, how the algebra retraction is coming out of these kind of maps. So this is one very important result in this particular context. F square is equal to identity. F square is equal to identity. So that is quite a cheap result, I would say. So you can think of, you start from A to B, but you are moving from this particular way. So the morphism is somewhere here, and A is somewhere already here, and your map is a kind of a cheat in the sense that you are going to from B to B, and restriction of F on A is already identity. Okay, and when you take and your F square is already identity on B, and this particular thing, this F defined in this particular, when you are going to have a morphism. So starting is inclusion map, this one. And the next thing is your phi. Your phi in this case is nothing, just your F in, and you have a retraction. I hope you understand the point, what Costa was trying to do. So it's all about how to construct this particular map. Okay. Okay, when any of the above mentioned equivalence condition of the property is satisfied, we say that F is a retraction of B. So I told you one of the central problem is to find ways to construct the retraction. So this is one of the important result which help us to give a retraction map. Moreover, this is a kind of a result which is saying which kind of algebraic properties are being preserved under the retraction. So if B is an integral domain and let A be a retract of B, then the following properties hold. Number one, A is algebraically closed in B. Okay. If B is a UFD, then A is also UFD. I hope there are few persons in the audience who are interested in the study of multiplicative ideal theory. So this is a kind of a result which is where people are trying to study different domains. So this is a well-known result. And if B is regular, then A is also regular. And another way of constructing the retraction is if let A be a retract of B and R is an A algebra. If A is a retract of B and R is an A algebra, in that particular case, AR is then he constructed this R, which is this one, is an A algebra retract of this particular. Now, by using a given algebra retract, you are constructing new algebra retract. by tensorizing the given rings. So you are seeing one result given by Costa in this particular direction, and there will be more like that in the upcoming slides. And moreover, there's a particular case of it. If J is an ideal of A, then A quotient J is an algebra retract of B quotient JB, provided A is an algebra retract of B. Okay. So one algebra retract is giving you the other. Yeah.
Yes, sir. Can you remind us what regular means?
Regular mean the maximal ideal is generated by the by the number of elements, the same as the Krull dimension of. Okay, this is a very special kind of ring, which I never seen before, and it was mentioned in the same paper of the Costa. They are called inert subring. If you are having a ring, and then again similar kind of work, I told you this is a good playground for multiplicative ideal theory persons. But here the inert ring subrings are really very important and very interesting. So inert subrings and retracts share many interesting properties. So first of all, what is inert subring of a given ring? A subring A of B is said to be is an inert subring, and with if and only if you multiply any two if you take any two members from B and you multiply if their product fall inside A, this implies that A and B are in A. This property is quite weird. It's not so trivial. So if any two product of the element is coming inside the smaller ring, then it means that both the members are also inside A. Then we call that A is an inert subring. So you may think about, this is a good time to think about even inert element. Yeah.
That A and B may be A or they are clearly in possibly.
Okay, please speak in the mic so that. Yeah. It is open.
Hello.
Speak. Yeah.
Yeah, you can listen me now. Okay. A ring is a trivially group. The clear law will be holds. So we are taking the subrings like A and B belongs to B, and particularly we say that if it is a subring and A and B belongs to B, if B is a
No,
subring.
A and B, you are taking the element
A
from
and
the
B,
bigger ring.
yeah,
bigger
yeah.
ring.
Yeah, and if these are the from the subrings, particularly the product will be in the subring. But now the property is having something more interesting that you say that the product is in the B, but we have to assume that the AB is in A, or they are
Both of them.
really, well, yeah, the elements A and B are in A, B, or we assume that they are in A. They are in A, or we
no.
have to assume
It
that they are.
implies that.
Okay.
Let me just write it down here for more clarity. So for instance, this is your bigger ring B. This is your smaller ring A, for instance. If you take any two, so it says that if you take any two members from B with the property that AB is inside A, then this particular thing implies that you pick A and B somewhere from A. Then we say that A is an inert subring of B.
Some kind of prime ideal.
Not necessarily. This is a good this is a good guess, but not necessarily. So if you talk about the prime ideal, okay, firstly think about the smallest element, 0. Does 0 has this inert property? No. So you can't think of even the ideals there. So inert subring has a very special crispy structure, and you will see many examples now.
Because there are also that if A and B on each A implies A, B should be in A.
If
reverse.
sorry,
We are already in A.
then definitely by the definition of subring, so AB should be inside A. So this is quite a reverse of it. If the product of the two members are inside A, okay, then it forces that both the elements are inside. Yeah, maybe next slides will open up some more examples. This is good that you are guessing about the inert subring. So this structure is very weird. Okay, now this is an element of, this is the definition of inert element. So if we say that uh, an element A is an inert element, if you are getting A for some xy coming from B from the product of the two, then those two element x and y, they are basically in A. So in that case, the product element is called the inert element. Okay. So this definition, inert subring and inert element, I hope everything is clear. Okay. Okay. This is one thing I already explained, that zero is not that zero is an inert element of A if and only if A is equal to B. So every ring is inert subring of itself. This is a trivial example, at least up till now you have. Okay, let's see more examples. Now consider the ring extension Z to Q and take any prime number P inside Z. Then the element P is inert in this particular extension, because if XY belongs to P, then XY is inside Q, then X is PY, and since PY must be an integer for X to belong to Z, so it follows that this Y in the denominator should be either plus minus 1 or plus minus B, plus minus B. So making X and Y both integers. I hope everything is clear. Okay.
In the zero example that you were giving us, you don't assume that it's an integral domain, right?
Sorry.
In the previous example, the zero,
Inert element, that you're not assuming that it's an interval domain, right? Or
Yeah, no, not necessarily. It can be integral or cannot be integral. But definitely this structure here under discussion, we are assuming the integral domains at the moment.
um, because so could you just go back a little one slide? Could you?
Oh,
go
yeah,
one
yeah,
slide?
yeah.
I want to.
This definition is generally for any ring, any
Yes,
ring.
I'm just the last statement. I
Uh,
was
the
just
last
trying to
statement.
understand
Okay.
this. So it's
Yeah.
okay.
Yeah.
So-
Even if it is not a domain, still it holds, I think, because zero divisors are already in that particular ring, right? This is your point.
Well, yeah, I guess I don't see why this is
Okay.
an if, but
If we take R is equal to Z6, and we know that 2, 3 is ZY. So I'm taking this one is the same as A and B. So definitely by multiplying, I'm getting 0, but 2 and 3 are already inside that ring, right?
yeah, okay. So
Uh, okay. Yeah.
Maybe we can put in condition that A should be integral domain, then zero will be in inert
Uh,
element.
if it is not an integral domain, that is I'm trying to say, get the property holds.
yes, okay.
Get the property holds.
Yeah, okay.
Interesting question. Okay, you want to see another example now? Oh, okay. Now think about this particular. I think this example is much more clear. Let R be a unique factorization domain, and consider the polynomial ring Rx. So if P is a prime element in R, okay, then P is an inert element in Rx, inside Rx. And this follows from the fact that Rx is also unique factorization domain. And this is the reasoning. Please see, if the product of the two polynomial is P, which is inside R, and in Rx, then both F and G must be associated with P inside Rx. So in that particular scenario, the situation is clear. This is uh, here we are talking about the inert element inside Rx. Okay, things are clear. Okay. Okay, then there is another important proposition. which says that let A be a subring of the unique factorization domain B, and why inert ring subring is important. This is due to this particular result.
Subring. So the product in the product X, Y shouldn't be one. Like one of them shouldn't be one, or it can be.
It can be. But the definition is coming from all possibilities. Right. This is a good observation when you are trying to construct an inner element, but you have to take all possibilities. As for inert element, please, inert element is this one. When you are saying that uh, a member of X is an inert element of the subring A, it means that you are considering all possibilities of A and B, which is giving you X. I hope this is clear. This clear, you are confused. Okay, yeah.
I'm having a hard time understanding
The first example, so if we have x times y is equal to p, suppose we set x to be 1/p and y is p squared. Then we have a multiplication giving us
X
p,
is 1/P
yeah,
and Y is,
p squared. So then their multiplication gives you p, right? And then now,
yeah. Okay,
but then we don't have that x and y are both in the integers.
let me just address this issue. Um, mhm. Uh, let's discuss this later on. Probably this is a point I
Sir?
didn't discuss. Yeah.
Y can only be P, not P scale, according to this condition. Can only take the value plus minus P.
No. He is trying to give an example which is not satisfying that particular condition. Not necessarily Y is plus minus one. That is the point of. Yeah. Let's discuss this. I think, but still, yeah. Still, this particular condition is still being valid. And let me just address it properly. So Y is either plus minus P or making X, Y both the integers. Let me just how to say that, how to address it.
The choice of Y is fixed here. We have four possibilities for Y.
Yeah, because p over y must be an integer here.
Yeah.
In case of 1/p, it will not be an integer.
Yeah, okay. Basically, in the example, he is trying to give a justification of this particular type. So you started from this particular idea. This particular thing is giving you P over Y. Okay. So in this case, we say that the claim is that P is an inert element, right? And it is only possible if X and Y both are belonging to P. Both are belonging to the integers. Now, from this particular condition, one construct what will be the value of X. So value of X, because this is an integral domain, so I can assume P over Y. Now, it is taking the possibility of Y, what Y will look like. So if any number which is divided by P, in order to have X as an integer, the only possibility is Y should be plus minus one and plus minus P.
What's the definition of inert element?
inert element says this particular. Let me just put it. Now I got the answer. Thank you very much for the clarification. So I say that A inside A is an inert element if the product of the two number which is giving you A, it forces X and Y is inside it. And you are taking X and Y for X and Y, you are taking from B.
So any X and Y.
Yeah.
Right, so.
And the idea, again, the justification is quite general. Now you assume that, again, the justification is quite general. We assume that there exists two elements whose product is P. Then from this particular description, I get X is equal to P over Y. So X is going to be P over Y. Now X is an integer.
We don't know. I agree with you. X and Y are equal.
X and Y, yeah, okay.
Each time one of them has to be one.
But we have to show.
Mm,
X and Y are equal.
yeah, okay. Now I got the issue.
Yeah, I think it's,
Yeah, it did say that. Yeah,
or maybe the definition is
so PY,
wrong.
If you go back to the definition of
mm,
inert element.
it should not be. So A is an inert element.
Have started with one element is belonging to the A. A is belonging to A. That's not. This is the reason that doesn't satisfy that.
This is the same, right? P is in A.
That
integer.
says that, okay, A is inside A.
Yeah.
But it didn't say X is inside it.
Yeah, that's what we don't
That's
know.
the issue. That's the issue. Yeah. Maybe we can address this issue later on so that we can complete this lecture. We can address this issue later on. Yeah, but this is quite an interesting problem. Yeah. I didn't notice that. This is an important point. Yeah. Okay. Why inert ring are so important? Because they are also giving us an retract. If A is an inert subring of B, so this is a condition which says that if and only if every non-zero prime ideal of A contains in an inert ring, and moreover, there are retracts which are not inert subring. So K be a commutative ring with identity. Then K is a retract of the formal power series ring, but it is not necessarily inert subring. So the topic is, again, we are coming back to the retraction problem. And there are particular example where there are not inert, but still the retraction is existing. And similarly, this is the second example where KXY is a retract of KXY under the given map. And this is obviously not an inert subring of it. KXY is not an inert subring of KXY. Okay, then there is an important theorem which says that let K be a field and A is an algebra retract of the polynomial ring Kx1 to Kxn, and the transcendental degree of A over K is 0, or A is equal to K. If the transcendental degree of A over K, okay, this is an important result in the context of proving that retraction problem. And basically, in this particular result particularly shows that Kx1 x2 is has an algebra retract of K. That proves the Costa problem for n is equal to 2. Transcendental degree is at the moment for your case, it's just the indeterminates. So indeterminates, yeah. Yeah, algebra. Yeah. So it is covering all the cases from having the Krull dimension from 0 to 2. 0 to 2. Do you understand? I think focus on this particular point. Focus on this particular point. The second part of the statement. Okay. And moreover, this is, I think the corollary make it further clear. Yeah, Ali.
This topic seems somehow strange. And that there can be a big APK of the one of the and the retract of K if the single value of A over K is zero and then
Let me, yeah.
A is
Yeah, I think it should be then.
then A.
Then A is equal to K. Thank you very much. That's a correct. It should be then. If then A is equal to K.
Okay.
Then it's okay. Thank you. Yeah, this is so important. You missed a then and this. Then. Okay. Okay, everything is clear now. Okay, let's move on. This particular construction is basically given by Herzog and Osugi in again during the year 1977, and it started with this particular construction. Okay, there are few interesting things. So now with this particular paper, I'm trying to give some important properties which is being studied under the algebra retract. So let S be a local ring with the residual field K, and let N be an S module. Then the Poincare series of N is defined as this thing. This is a quite a standard Poincare series description, or in other words, you would like to take it as a Hilbert series. And then there is an important theorem by Herzog in 1977. I believe this is in his PhD thesis. That let J be R to S be an algebra retract if there exists an algebra retract, and let M be an R module. I repeat, R to S has an algebra retract, and M is an R module as a module over this particular ring. So if we consider M to be an S module under the retraction map, this particular map, then we have this particular relationship satisfied between the Poincare series of M over S, and satisfy this particular condition. Then the second important description, which is given in that particular paper, is that a special algebra retract given by the, okay, this slide is important if you would like to construct the algebra retract, and how you can construct algebra retract. And this kind of construction is given by Herzog, and he called it the trivial extension by using the trivial extension. So a special class of algebra retract is given by trivial extension, and let R be a local ring and N be an R module. I repeat, R is a local ring and N is an R module. Then R tensor N, whose elements will look like that, R, and it consists of a similar kind of, he represented in the form of the pairs, where R is coming from the ring and N is coming from, so it's backslash N. N inside N. So addition is the usual component wise, but multiplication is is given by this particular way. So if you are going to multiply R1 N1 with R2 N2, so this is this one you are getting. Okay, this particular extension is called a trivial extension of R by N. So this is the definition of trivial extension of R by N, given by Herzog in that paper. And we have a natural mapping from J to R. This is important. J is taking from R to R. So now he is trying to construct the retraction map. So this is a simple embedding of R inside R tensor N under this particular map. And now this is the projection map. So which is sending R tensor N to R by using this particular map. And when you take the composition of these two, it is easy to see that the composition is the identity of R. So ultimately you constructed a retraction from R to R tensor N. So whenever you have so one can construct retraction by just following this particular procedure and by using this trivial extension. So this map is, I hope everything is clear with this particular map. And this is a theorem. So from that particular paper, there was a general method. One can construct algebra retract by using the trivial extension. So then this particular theorem, okay, these results are really important in the context. Okay, when we have been addressing this type of question when there exists an algebra retract between A and B, and the answer can be yes and can be no. So in order to address this particularly when I would like to say that there does not exist an algebra retract, again, by saying that it is a not so trivial problem. I repeat, declaring there does not exist an algebra retract between A and B is not a simple problem. How to attack this kind of problem? So in order to attack this kind of problem, there are particular results which really help us. So one of this particular result is this one. Uh, One of this particular result is given by Herzog and Osogi and Hibby, which says that if let R is inside S be an algebra retract of K algebras, then we write R as and R is a quotient ring of this particular type, and S is a quotient ring of this particular type, B quotient J. So where A and B are the polynomial ring over K, and I and J are graded ideal containing no form of degree 1, then for the graded Betti numbers, so if there exists a retraction from R to S, then the graded Betti number of this ideal I and the graded Betti numbers of this ideal J has this particular relation in between. So the graded Betti number of J will supersede, and this is not only the Betti number, it is about the graded Betti numbers. So how this particular result help us? So for instance, we have an inclusion map. So whenever we have an inclusion map, so there is a natural question whether there exists a retraction or not. So for addressing this particular problem, you should have an inclusion map first. So wherever the inclusion exists, then the question for arises for the retraction. And this particular result help us says, so if I compute the graded Betti numbers of I, and I compute the graded Betti numbers of J, and if it satisfies this particular result, it didn't say anything. I repeat, I am undecisive whether there exists an algebra retract in between them or not. But for the negation, if for some particular I or J, we have this particular relation at any stage, so we say that there does not exist any algebra retract between the two structures. So that's the main point the people are addressing, that okay, declaring there exists an algebra retract, it means you have to construct a map. You have to show the map is there, which is satisfying the property of algebra retract. And in order to declare there does not exist an algebra retract, in that particular case, this result is the most important. The most, not the most, is one of the important result. That is the end of this lecture. And uh, I need to, to address that particular example later on. So probably we can. So are there other questions? So we can take those and then we can come back to that example to figure out.
Is there any other question?
Yeah. Yeah. So, graded Betti number. Okay. Big story. So for any ideal, if ideal is graded inside the polynomial ring, it has a free resolution. So a bit long story. So regarding to free resolution, uh, so for instance, going with I, we have 0. So free mean that at each step you will be getting the free module, and these free modules will be of this particular type, and there will be some shift available. So um, so there will be some powers appearing there, and some summations will be appearing. And this is called the free resolution of any ideal or any module. And just recording the shift at each level and the count. This is the way we measure the graded by D number. And yeah, it's a big story of scaling. We can discuss it later on with some example. Yeah, Abbas.
Uh, I have a question about the Zariski cancellation problem.
Zariski cancellation problem.
Okay, this theorem holds for if you replace polynomial ring with formal power series or convergence power series.
This particular problem is exactly in this particular form. So in this particular case, only for the polynomial ring. You would like your point
I
is
would
if you
like to
can,
know if there is another results if you replace polynomial ring with formal
I
power
didn't
series
know. I
or
don't know.
convergence of power series.
I don't know about that.
Okay, and
Probably I have seen the problem only in this particular context.
okay.
Probably there may be other variant exists in the forward power series.
And also, I cannot understand geometry of this theorem.
Sorry.
Geometry of this theorem, the Zariski cancellation theorem. Do you know what does mean geometrically in algebraic geometry?
Mm, I only see the algebraic aspect, but geometrical aspect I didn't see. But I think people have written surveys on somehow this is the most ignored problem, kind of.
No, okay.
And I think recently when Nina Gupta gave a counterexample or cancellation of this particular problem, that all in a sudden it come to the light once again. Because many people, including myself, always think that this holds. There's no harm. Just like many people are thinking that seems to be quite trivial problem, but this is not so trivial. Proof does not exist here. Yeah.
Thank you.
Sorry, could you just give a little bit of intuition to why it's so difficult to find an algebra retract?
Somehow I try to, okay, for the negation, the problem is okay. You understand? If I say that there does not exist any algebra retract inside inside this structure, declaring there does not exist is not an easy problem, because probably you are trying to find a map and you are unable to find, but it doesn't mean there does not exist. So negation, by saying that there is an inclusion and there does not exist an algebra retract, is not so straightforward until unless you can show that if A is an algebra retract of B, then they are forced to satisfy a certain condition. If that condition is violated, then you declare this is a no. In case of yes, constructing the phi is the biggest question. So it is really very hard to construct that phi. So in few examples, you have seen that the phi is constructed, and even the result you have seen, even in the paper of the Costa and other, there are people are trying to construct phi, and their construction are completely independent of each other. So in the upcoming lectures, you will see more of the work. So probably the good thing is the construction given by Herzog. Probably this one. This is one way of looking at building the retraction. So this is a kind of a trivial way, but in general, we came across these kind of scenarios a lot. And this problem has multifaceted in the sense that, for instance, this J is coming from a combinatorial structure. For instance, simplicial complexes. For instance, coming from a graph. For instance, coming from a hypergraph. And this I is coming from the subgraph of that graph or subcomplex of that particular complex. So the problem translated into many directions. And again, problem is always this pi. And for specific example, one can construct. But if you are trying to address a problem in general, this is not so easy. But I hope you understand. But Zariski cancellation problem is quite a celebrated problem. And one can find a lot of literature around discussing it where people are, I didn't discuss the algebraic geometry approach, but there do exist. People are trying to attack this problem from the algebraic geometry point of view by using different tools. I never seen the blow ups there. Probably they might be
yeah.
they might be using blow ups as well. Uh,
I can't understand this.
maybe
Well, I can't understand the statement of the last term. Can you?
yeah. It
go-
Ali, it can be understood here.
Yeah. no,
If there
here
there's an
You mean S is algebraic retract of R, or R is algebraic retract of some polynomial ring, and S is the algebraic
Of
retract
some other-
other.
some other problem. So in any case, if I replace it, for instance, with S, and still we have a similar kind of inclusion happening there, and still this result hold. Okay, this is really, thank you very much for bringing this point. This is really not necessary. You are dealing with the same ring. And you know the problem, combinatorics, when you go from a simplicial complex to the subcomplex, you reduce the variable. So sometime this A is not exactly the same B. So when Herzog was giving and Osogi, so they were trying to capture all possibilities. Otherwise, it was easier to use A in both sides.
So, assume that we have two simplicial complex, and we know that both simplicial complex are algebraic retract of polynomial ring.
Sorry, repeat again.
Assume that we have two simplicial complexes,
Okay.
and we know that the Standard-Reisner ring.
So regarding simplicial complex, I would say that you should wait for the next lectures. So in the next lecture, I will take this particular problem to the simplicial complexes, and moreover, in the cut algebras, the work of Sarah with Tim Romer, I will touch that particular guy. But that example is still open. We need to address that. I didn't bother much about that. Are there any questions from this?
Question from the online audience?
I have a question.
Yeah.
So what does it mean by IJs or radials containing no form of degree one? Is it is it
Oh, sorry, Javed
मैं-
बोल रहा हूँ. I was trying to understand कि ये उधर Javed
Yeah.
क्या Okay.
is it addressing about its generators? It contains no generator of degree one. What does it mean by no form?
No form of it just says that in the generator there is no variable appearing.
Yeah.
So he avoided that particular result for probably they might be facing some technicalities of losing some information.
So, as Dr. Ali was saying, simplicial complex. So there is a chance we have an isolated word.
Yeah, isolated verb. In that particular case, this result doesn't value. Yeah, exactly.
Okay.
I thought that someone is
there
asking
any
from
other
that.
question from IB or online audience? Are there any question in the chat box? No? Okay. So if this is the case, so let's thank the speaker again.
Thank you.
I would like to answer that question.
Would you like to?
No, not this one. On the board.
Oh, probably I need to. You would like to answer?
UFT. Every field is UFT factorization to me. So that's why when you are writing this thing, But that is unique factorization to me. So you can always write in this. Because p is a prime number, so there are only two factors, plus minus one and plus minus p. That is the vector. That's why that is what is called.
Associated, associates. Do you understand what it was trying to say? Let me explain once again.
Discuss later.
Maybe later on. Yeah.
But you have time another. Okay. Let's start the speaker.
Next week.